Hello, my name is Lorenzo Dall'Amico, and this is a presentation of the work of my PhD thesis on spectral methods for graph clustering, which is joint work with my supervisors, Romain Cuillet and Nicolas Tremblay. First of all, I'll try to explain what spectral methods for graph clustering mean, and in particular, I'll focus on the problem of community detection. So clustering methods are unsupervised algorithms for data categorization. To visualize this, the idea is that we have a data set of which we only have some partial information. And the goal we have is to divide the objects of this data set into similarity groups so that elements that are assigned to the same group are somehow similar. In this example, we put together what says meow with what says wolf. I would like to underline the fact that even though deep inside we know that these two classes correspond to cats and dogs, the solution of clustering is red and blue question marks. So we are able to make two groups, but we do not know to what these two groups correspond. Unsupervised methods means that the only available data we have are the data themselves, and we do not have any further label or training. So what we have to do is to define an algorithm that somehow lets the data speak. What we should keep in mind when we are performing this task is the feature extraction and clustering paradigm. The input data are some complex objects that live in the real world, such as apples and pears, or in the example of the earlier slide, cats and dogs, which must be translated into a simple mathematical equivalent. To do so, we associate a vector of features, feature vectors, to each of the input data. In this example, it could be a vector in which we store the values of the weight, the volume, the number of calories of each fruit, and it maps each of the input data to a point in a multidimensional space, which we call the feature space. If the feature we chose are significant, then similar objects in the initial space should be mapped to nearby points in the feature space. And once we have done that, we can cluster together points that are close by. This is a very fundamental aspect of learning because the identification of the most important features, of the discriminant features, allows us to define the concept of categories themselves and to define the objects. Now, what we do, however, is graph clustering, which is a particular case in which we consider as an input a graph, which is a ubiquitous object able to represent pairwise affinity. Affinity here is written in inverted commas because is intended within a very wide sense. Affinity may mean geometrical proximity or friendship or collaboration. Each node of this graph is represented as a dot, and it is an item, a person, a city, and the edge is the line connecting them, is a sort of relation there is between these two nodes. And what we want to do is to create a mapping of each node into a feature space so that nodes that are similar on the graph should be mapped to nearby points. Now, the basic idea we want to exploit is the fact that a graph has a natural way to be represented as a matrix. G is the graph, V is the set of vertices or nodes. We say that there are n nodes, and E is the set of edges. Then we define the adjacency matrix, which is a representation of the graph, as the matrix of size n times n, the number of nodes, so that the entry ij is equal to 1 if there is an interaction between node I and node j, and is equal to 0 otherwise. Equally important is the diagonal degree matrix, whose entry ii corresponds to the number of connection node I has, and we call this number the degree of node I. To visualize these two matrices a bit better, we consider this simple graph with the 5 nodes, and on the right, the corresponding adjacency matrix. If we highlight the rows and columns corresponding to node 1 and 4, we see in blue the crossing between the entry 1, 4 and 4, 1, which is in this case a 1 because node 1 is a neighbor of node 4. On the opposite, if we consider 1 and 3, at the crossing in blue we find a 0 because node 1 is not a neighbor of node 3. Repeating this little game for all entries, we obtain the adjacency matrix, which I repeat is a representation of the graph. Now, the degree matrix, as I mentioned, is a diagonal matrix. The first entry is equal to 2 because node 0 has 2 neighbors, whereas since node 1 has 3 neighbors, the second entry is equal to 3, and so on for all the remaining. Now, the basic idea behind spectral clustering is that we have a graph, which is our input data. The graph has a natural way to be represented as a matrix. We saw the adjacency and the degree matrix in the earlier slides. And once we have a matrix, we can compute its eigenvectors, which are a property of the global structure of the matrix. So somehow it's something that the matrix, hence the graph, tells about itself, which is precisely what is the spirit of unsupervised methods. What we do is we use the eigenvectors of this well-suited matrix to extract the node embedding, the node feature extraction. Now, the typical spectral clustering algorithm can be written in this form. I underline the word typical because not all spectral clustering algorithms can be written in this way. The ones we proposed are not written in this way, but this gives an idea of what is the procedure to follow. The input is the graph, and K, the number of clusters. Then we choose the matrix M, which is a suited matrix representation, graph matrix representation. Actually, one of the main goals of spectral clustering is to identify the correct matrix M, which may or may not be the adjacency matrix. Then once we have the matrix M, we compute K of its eigenvectors, and we store them in the columns of a tall matrix X of size n, the number of nodes, times K, the number of clusters. Each row of this matrix corresponds to a node and is a vector in K dimensions, which is the feature vector. Once we have projected each node to a point in a multidimensional space, then we can run some clustering algorithms such as k-means, and we return the labeling vector. Now, the presentation I propose today is mainly focused on a particular application of spectral clustering, which is community detection. But during my PhD, we touched also other topics more in depth. Namely, we gave a unified framework for several algorithms, competing algorithms of the spectral clustering, and we are able to understand them under a unique framework indeed. Then we worked on the problem of efficiently implementing the proposed algorithms and providing an open source Julia package to do so, which is called CodeBefe. Then we studied the problem of dynamical community detection and spectral clustering on weighted graphs as well. But today, I repeat, we will mainly focus on the problem of community detection. So what is community detection? The idea is that given a graph, we want to find a partition of the nodes to recover the community labels. This is a bit tautological because what are communities after all? The easiest way to visualize this problem is to think of a social network in which we have groups of friends, groups of colleagues, groups of people sharing some similar interests that interact more often among themselves. So we have a graph in which we have groups of nodes that interact more often, and we want to recover the community given the graph. So this is the problem of community detection 101. The input is the graph or its adjacency matrix representation on the right, where each purple dot represents a 1 and each white dot represents a 0. And the solution is the one I show in this slide. So each node has a color code, which is the label, the community label. And on the right, we have the same adjacency matrix in a basis so that nodes that are in the same community are close to one another. And we can clearly see that nodes in the same community interact much more often than nodes across community. So this is the basic idea behind community detection. Now, what is spectral clustering for community detection? I recall we have to define a matrix M of which we will compute k eigenvectors that we use to make the feature extraction of the nodes in K. Typical choices of the matrix M are the adjacency matrix itself, I mentioned before, D minus A, the degree minus the adjacency matrix, which is called the graph Laplacian matrix, or some sort of normalized Laplacian matrices. These are very popular choices and also historically very relevant. However, they show poor performances on graphs that are sparse and heterogeneous. Sparsity means that the average number of connections each node has is very small compared to the size of the graph. This is typically observed in real-world graphs, as we will see in the following slides. Whereas heterogeneous means that each node may interact with a very different number of neighboring nodes. So we may have few nodes that interact with a lot of nodes and others that interact with very few nodes. These two aspects are observed in real graphs and are problematic for the popular choices of M in spectral clustering. Now, coming back to sparsity, this is a collection of datasets, real-world datasets. The second column indicates the size, so n, the number of vertices, that goes from 62 to 36,000. And the third column is the average degree, the average number of connections each node has, that goes from 5 to 10. We see that having a large graph does not mean to have a large average degree, and this is true even for graphs that have millions of nodes. If you double the size of Facebook, you won't double the number of friends you have on Facebook. So real graphs tend to be sparse. Why is this a problem? We can visualize it easily looking at the spectrum of the matrix M, which is in this case the random walk Laplacian matrix D-1A. This is for a dense graph, so unlike commonly observed real graphs, for k equal to 2 clusters. So we have two eigenvalues of this matrix, which are in red. We call them isolated because they have they're not degenerate, whereas all others are drawn in green, and they are almost degenerate. We can plot a histogram, and we call them the bulk eigenvalues. So I recall that in a spectral clustering algorithm, what we have to do is to compute k eigenvalues of the matrix M. In this example, we would compute the two red eigenvalues, the two isolated eigenvalues. Now, as a rule of thumb, if we have k isolated eigenvalues and k classes, then the spectral clustering algorithm is likely to work well. However, if we have a sparse graph, so what we observe typically in real networks, what we see is that the bulk is much broader and one of the two isolated eigenvalues is disappeared. So here we have two classes and only one isolated eigenvalue, and this is bad news, and it's the reason why typical choices of the matrix M do not work properly on sparse graphs. If we come to heterogeneity instead, it has been observed that often it happens that we have, as I mentioned earlier, few nodes that are called hubs that interact with with a large number of the nodes on the network. Think of a Twitter account of a politician, whereas we have most nodes that have a very small degree. This broad degree distribution is often observed to be a power law distribution. What is the effect on spectral clustering? In this slide, we show a spectral embedding obtained on the left on a network with a homogeneous degree distribution, and on the right on a power law degree distribution. So on the left, what we see is that the color corresponds to the community assignment, And we see that similar nodes, so nodes with the same color, are mapped to nearby point in the feature space. So the embedding we obtain on the left is perfect. It's exactly what we want. The moment instead in which we have a power law degree distribution, on the right, we see that the size of each point is proportional to the degree of the node. And we see that nodes with a small degree are mapped to nearby points in the feature space. So they're all close to the origin of the feature space. And this is a problem because what we want is that nodes with the same color are mapped to nearby points, not nodes with the same degree. So what we have on the left happens on networks with a homogeneous degree distribution, which are not typically observed in reality, but is very good. Whereas what we have on the right is what we would observe typically on real-world networks, which is problematic because nodes that are similar are not necessarily mapped to nearby points in the feature space. Now, in order to keep into account of both of these very challenging features, so heterogeneity and sparsity, we use a random generative model called the degree-corrected stochastic blob model, or in short, DCSBM, which is capable of capturing the community structure of a graph, its sparsity, and its heterogeneity. These three aspects are not the only three that characterize real-world networks, but they are possibly the most challenging for spectral clustering. So each edge of the graph of the adjacency matrix is generated independently at random, and an edge between node I and node J is created with a probability proportional to theta I, theta J, where theta I is the intrinsic probability that the node I has to get connected. Is an intrinsic probability because it is not normalized, but its average is set equal to 1, its second moment is set equal to 5. With this vector, we have that the expected degree of I is proportional to theta I, and so the vector theta can reproduce an arbitrary degree distribution. The broader the degree distribution, the larger the value of phi will be. So we have a network with a heterogeneous degree distribution. Then we have the community part, which is created with the matrix of size k times k, where k, I recall, is the number of classes. And the entry CAB of this matrix indicates the affinity of the nodes in class A and the nodes in class B. A node in class, the connection between node I and J is produced with a probability proportional to CLI LJ, where L is the label vector. And finally, the term 1 over n, the number of nodes, makes it so that the expected number of connection each node has, the expected degree of each node, is independent of the graph size, and this is precisely the definition of sparsity. Given an observation of A, which is a random variable, the objective of community detection in the DCSBM is to infer the vector L, so the hidden parameter of the generative model. Now, this task cannot be achieved for all values of the input data. In particular, there is a detectability threshold. If we consider the case of k classes of equal size and the matrix C written as C in on the diagonal and C out on the off diagonal, then there exists a parameter alpha, which is a function of C in, C out, phi, the broadness of the degree distribution, and k, the number of classes, so that if alpha is less than a critical threshold alpha C, then detection, which is reconstruction of the vector L better than random guess, detection cannot be achieved in polynomial time. Why is this relevant? Because spectral clustering algorithms are based on the computation of matrix eigenvectors and are polynomial in essence. Hence, if we recall our rule of thumb that tells us that if we have k classes and less than k isolated eigenvalues, then the spectral clustering algorithm is unlikely to yield a good performance, then what we can say is that what we expect to observe is that if alpha is less than alpha C, we should not find a matrix M with k isolated eigenvalues. But what we want to have instead is that if alpha is greater than alpha c, then we want to observe these k isolated eigenvalues. This is the detectability threshold. Unfortunately, typical choices of M do not achieve the alpha c threshold. Now, the objectives we have in mind is to define a new spectral clustering algorithm which is inspired by the DCSBM, which allows us to have a very deep theoretical understanding, but it is applicable to any input graph, which is capable to deal at once with sparsity and degree heterogeneity that are two challenging and frequently observed aspects of real networks. And finally, that on DCSBM graphs, it's able to achieve the detectability threshold, which means it's able to go as far as it is possible to go. To do so, we build on some physics-inspired methods, and notably on two matrices, very closely related matrices, which are the Bethe-Hessian and non-backtracking matrix. To understand the Bethe-Hessian, we must first talk about the Hessian model on the graph G. So we assign to each vertex of the node of the graph G a spin variable, 1 or minus 1, which can be thought of as small magnet. And the Hessian Hamiltonian is a cost function, is an energy function, that for each pair of neighboring nodes assigns a weight equal to -1 if the two spins, if the two magnets are aligned, and a weight equal to +1 if the neighboring spins are misaligned. In other words, we have to pay a cost each time two neighboring spins are misaligned. And the energy favors configurations in which neighboring spins are aligned. Now, the smallest energy configuration is the so-called ferromagnetic configuration, in which all spins are aligned. However, if the graph G has a community structure, we expect to observe low energetic configurations in which all spins in the same class are aligned, because the majority of the spins in of the nodes in the neighborhood of a given node are expected to have the same label assignment as the central node. Hence, the term in the sum is expected to be negative on average. Now, in physics, however, we do not stop at looking at the Hamiltonian, but we consider the free energy. To explain and understand in few words the free energy, it is the competition between two terms. One is the internal energy, which favors configurations in which we have a small energetic cost, because we do not have to pay the energetic contribution to have a disordered configuration, and the entropic contribution. In fact, even though the ferromagnetic configuration has a very low energy, so a very low cost to pay, there is only one way in which order can be obtained. Whereas if we consider a random configuration, it has a much higher energy, but there are almost infinitely many ways of obtaining that configuration. The balance between these two terms is governed by the temperature T. At low temperature, we want to minimize the energy. At high temperature, we want to maximize the entropy. As a consequence of the fact that we expect to have low energetic configurations induced by the community structure of the graph, then also the minima of the free energy are expected to be informative. Now, the way in which we want to retrieve this minima of f of m uses the eigenvector of the so-called Bethe-Hessian matrix, which is obtained in with the following procedure. We have the Hessian Hamiltonian, which I just defined on the graph G. Then we introduce a temperature-like parameter R, so large values of R correspond to large temperatures. We perform the beta approximation, so we do not compute exactly the free energy, but we compute an approximation of it. We compute the Hessian of this beta free energy at the paramagnetic point, and we obtain the Bethe-Hessian family of matrices, which is given by R squared minus 1, the identity, plus D minus R, the adjacency matrix. Where R, I recall, is temperature-like parameter greater or equal to 1. Now, as I mentioned, we can use the eigenvector of this matrix to approximate the minima of the beta free energy. And in particular, here we have a graph with two communities. If we look at the eigenvector associated to the smallest eigenvalue of the beta Hessian matrix HR for a fixed value R, then this eigenvector is associated with the ferromagnetic configuration. So all its entries have the same sign. Whereas if we look at the eigenvector associated with the second smallest eigenvalue, it is a configuration which all spins in the same community have the same sign. I would like to stress the fact that here we have two classes, k equal to 2, and two isolated eigenvalues, even if the graph is sparse. Closely related to the beta Hessian matrix is the non-backtracking matrix, which is defined on the set of directed edges of the graph. And the simplest way to visualize its definition is by considering once again the simple graph. Now, we have to map each directed edge of the input graph into a new node. So node 1 is connected to node 4. We will find a vertex called 1, 4 and a vertex called 4, 1. And then we connect the vertices of this new graph if on the original graph we have a non-backtracking path between these two vertices. So a non-backtracking path allows us to go from node 4 to node 1, and then from node 1 to node 0. So 4, 1 will be connected to 1, 0, but it does not allow us to go from node 4 to node 1, then back to node 4. The non-backtracking matrix is the adjacency matrix of the graph on the right. Now, I said these two matrices are closely related because due to the Yarabas formula, if R is an eigenvalue of the non-backtracking matrix B, then the matrix HR, the beta Hessian matrix, has an eigenvalue equal to 0. The spectrum of the non-backtracking matrix B on DCSBM graphs has been studied thoroughly and rigorously, and in particular, it is a non-symmetric matrix, hence its eigenvalues are defined on the complex plane. For a graph with k communities, however, we have k isolated real eigenvalues outside its bulk that are here plotted in blue, while all others are bounded by circle in the complex plane operates the square root of rho b, where rho b is the leading eigenvalue of b. This happens as soon as alpha is greater than alpha c. I recall that for alpha less than alpha c, we do not expect to have k isolated eigenvalues, whereas for this matrix, as soon as alpha is greater than alpha c, we have k isolated eigenvalues, which is essentially the best we can hope for. Similarly, for the beta Hessian, it has been studied for a specific value of r equal to the square root of rho b, so the radius of the bulk of the non-backtracking matrix, and it has been shown that for alpha greater than alpha c, we have k isolated negative eigenvalues, while all eigenvalues are positive. Also in this case, we have k isolated eigenvalues as soon as alpha is greater than alpha c. So these two matrices, h of square root of rho b and b, are a very important, a very strong choice of the matrix M because they achieve the detectability threshold alpha c. However, they do not keep into account for the degree heterogeneity, in the sense that if we use the corresponding eigenvectors to produce a node feature extraction, it will be affected by that effect I showed in one of the first slides, in which nodes with a small degree will be likely mapped to nearby points in the feature space. So the questions we asked ourselves is, first, is there a way we can use these matrices to deal at once with sparsity and heterogeneity? Second, is there a value of R which is different from square root of rho b, which is capable to achieve this task, which works better than the initially proposed choice? And finally, if it exists, is there a simple way to estimate it? The answer to these questions are the central contribution of our work, which consists in the proposition of an optimal Bayesian parametrization. It's studied on the DCSBMs. Then we proposed, based on these results, an algorithm which is tested and then interpreted. Now, the main idea is, what is the optimal value of R at which the matrix HR should be considered? In other words, what is the optimal temperature at which our problem should be set? Now, the next definition that will come will have a notation which is not very intuitive, but we will walk through these definitions in the next slide a bit more carefully. So with this notation, lambda p a power of m, we denote the pth smallest eigenvalue of a matrix. And we define the zeta p, if it exists, as the smallest value of R greater or equal to 1, so that the pth smallest eigenvalue of the Bayesian matrix HR is equal to 0. Before trying to understand what this definition means, let me first stress that it is well defined on any graph G, so it does not involve the DCSBM assumption at this level. And secondly, the zeta p's are a property of a graph. You give me the graph, I can compute the zeta p's. And in the spirit in which an unsupervised algorithm has to let the data speak, well, the zeta p's are something the graph is telling about itself. Now, to understand a bit better this definition, we will look at this graph. We will consider this graph, which is made by 4 clicks and some extra edges. And this is a graph which has undeniably 4 communities. So I plot on the x-axis the value of R, which goes from 1 to 2.5 approximately, and on the y-axis, the 6th smallest eigenvalue of the matrix HR. Starting at R equal to 1, the smallest eigenvalue is equal to 0, all others are positive. Then when we increase the value of R, the first one becomes negative, and the following decrease until eventually the second hits 0. This is precisely the value of zeta 2. Then the same fate happens for the third and the fourth eigenvalue, and these are the definition of zeta 3 and zeta 4. For any value of R, we see that the 5th smallest and all the subsequent eigenvalues of HR do not cross 0, hence zeta 5 and all the subsequent zetas are not defined. So I repeat, zeta p is the smallest value of R, so that greater or equal to 1, so that the pth smallest eigenvalue of HR is equal to 0, and they correspond to these 4 vertical lines. Now, exploiting the Yarabas formula, we can also say that the zeta p's are eigenvalues of the non-backtracking matrix. To visualize this, we have a very similar plot to the one I just showed on the left. This time we start from the right, from a much larger value of R, so R equal to 12, and we go backwards. Whereas on the right, we have the spectrum of the non-backtracking matrix of the graph. So at the beginning, all eigenvalues of HR are positive until the first one becomes negative when R is equal to the leading eigenvalue of B. Then the second becomes negative when R is equal to the second largest eigenvalue of B, and then the third, and then the fourth. These are the k leading eigenvalues outside the bulk of B that have been studied thoroughly for the DCSBM and that I mentioned before. Then these 4 eigenvalues become back positive, as I showed in the slide just before, when R is equal to zeta 4, 3, 2, and 1. So the zeta p's are isolated eigenvalues inside the bulk of the non-backtracking matrix. Now, everything I said so far is true for any graph, but we can go a bit further considering the DCSBM assumption. First of all, the largest p for which zeta p is defined is k, and this allows us to estimate the value of k. In the earliest example, we had a graph with 4 communities. Zeta 4 was defined, zeta 5 was not. Then we have also conjecture on the asymptotic position of the zeta p's, and in particular, this is given by rho b, the leading eigenvalue of the non-backtracking matrix, divided by the pth largest in modulus. To visualize this a bit better, here we have the spectrum of the matrix B for k equal to 2 communities. The second largest eigenvalue in modulus is highlighted in red, and zeta 2 also is the one inside the bulk. We plot this spectrum for different values of alpha. Alpha, I recall, is the hardness. Large values of alpha are easy problems, whereas when alpha goes towards alpha c, then we do not expect to be able to see k isolated eigenvalues. So as alpha gets smaller, so the problem gets harder, the second leading eigenvalue goes towards the bulk and zeta 2 as well until they meet at the transition alpha equal to alpha c. This tells us two things. When we have hard problems, we have a large values of zeta p, and zeta p, I recall, is the value of R, which is a temperature. Hard problems means high temperature, means to give more weight to the entropic contribution of the free energy. And secondly, zeta p exists if the eigenvalue outside the bulk of B exists, because they are in one-to-one relation. And these eigenvalues exist as soon as alpha is greater than alpha c. So we claim that the zeta p exists as soon as alpha is greater than alpha c, which is the best we can hope for. Now, why are the zeta p so important? Because of xp, which is the eigenvector associated with the zero eigenvalue of this matrix. For simplicity, let's consider the case of two classes where sigma is the label vector, which takes value either 1 or -1. Then what we claim is that the eigenvector x2 is a close approximation of the vector sigma for any degree distribution. Now, sigma is the perfect feature extraction we want for this problem. In fact, it maps nodes in the same community to the exact same point in the feature space. And if x2 is a close approximation of the vector sigma, then the feature extraction obtained with the vector x2 will be a good feature extraction. This for any degree distribution. This argument is also valid for k greater than 2, but is a little more involved to present, and I leave it for the moment. Now, to visualize this a bit better, here we have the vector x2 on top for the choice r equal to square root of rho b, so the one initially proposed, and on the bottom for r equal to zeta 2 for a power law degree distribution. The background color is the ground truth label assignment. The size of each dot is proportional to the degree of that node. And on the right, what we can see is the histogram of the entries of this eigenvector, which is maximal on top around 0, because all nodes with a small degree are mapped to nearby points in the feature space. Now, why is this a problem? Because the moment in which we want to apply clustering algorithm, what we have to do is to define a line that separates what is above from what is below. And this line happens to be in the region of highest density of points. Hence, the slightest mistake in identifying this line will lead to the misclassification of a large number of nodes. This does not happen in our case, in which the vector x2 is actually a good approximation of the vector sigma, and around 0 we have a minimum of the density of points. Hence, this feature extraction actually maps similar nodes to nearby points in the feature space. Given these results, we have an algorithm. We take as an input the graph and the number of clusters k. For p that goes from 1 to k, we compute zeta p, and then we store the vector xp, eigenvector xp, in the column of the matrix X. Given this, then we perform the cluster in k dimension, and we return the label assignment. I would like to stress the fact that here we are not computing k eigenvectors of one matrix, but we have k matrices, h of zeta 1, h of zeta 2, h of zeta k, each one contributing with only one eigenvector, the one corresponding to its zero eigenvalue. From a practical viewpoint, implementing efficiently this algorithm has some challenges. The first one is associated to the value of k, which is typically not known in advance. But as initially suggested in SAD 2014, we can estimate this value of k as the number of negative eigenvalues of the matrix of the beta-Hessian matrix for R equal to the square root of rho B. However, the efficient implementation of this was left as an open question. We solved it using random projections and a polynomial approximation, which works particularly well, especially when we have large values of k. But now we also focus more in particular to the problem of how to estimate the values of zeta p efficiently. Now, zeta p is nothing but the solution of a simple equation like lambda p of HR is equal to 0. But a grid search is inefficient because each time we have to evaluate this function for a different value of R, we have to compute p eigenvalues. And this has a complexity which scales as the number of edges times p squared. So we must find a way to evaluate this function the smallest number of times as possible. To do so, we have an iterative method. Zeta p is the vertical line, it is the value we're trying to find. RT is an initial guess we have, which must be greater than zeta p. So RT for t equal to 1, for instance. Then the purple line is lambda p of HR is the actual function of the p smallest eigenvalue of the matrix HR. Then given RT, computing p eigenvalues of the matrix HR, so this is the computational heavy part, we define a function f of RT of R, which is the green line, which is strictly superior to lambda p of HR. In a very cost-efficient way, however, we can find its 0, which is the blue dot, and we update the value of RT to the 0 of this function. We define a new function f of RT, then we update the value of RT to the 0 of this function, and in this case, we obtain convergence in approximately 3 iterations. So we are able to compute all the zeta p's in a very efficient way. Given the algorithm, then we tested it. First, we show the result on synthetic graphs. So we show the performance in terms of overlap with the ground truth label assignment, L. Overlap equal to 0 means that we are reconstructing the vector L as well as random guess. Whereas when the overlap is equal to 1, we have a perfect reconstruction. Alpha, I recall, is the hardness of the problem. Big values of alpha means an easy problem. Alpha less than alpha c means that the overlap cannot be asymptotically positive. On the left, we have 2 communities. On the right, we have 5. So starting from the bottom, we have some stars, which is the performance obtained by the random walk Laplacian, which is one of the first matrices I showed at the beginning as a typical choice of spectral clustering matrix, which performs very poorly on sparse graphs and is unsuited for this setting. And then we have in yellow the adjacency matrix A, which does not achieve the alpha C threshold as anticipated, but even when the overlap is non-zero, it is far from being optimal. In green and in red, then we have the non-backtracking and beta-Hessian matrices, which do achieve the alpha C threshold, but the away are suboptimal when alpha is away from the transition. We are the blue diamonds. We achieve both the transition and obtain very good performances away from the transition, and we obtain the best performance among all spectral clustering algorithms. A short word should be done on the black dots, which is regularized Laplacian, which obtains a very close performance to the one we obtain. I will come back to this matrix in a few slides because we have a clear interpretation of why the performance of this algorithm is close to ours, because there is a clear connection between the two. Finally, the pink triangles are belief propagation, which is not a spectral algorithm, but is on this particular problem, the asymptotically base optimal solution. So what we can see is that at the smaller computational cost, we are able to achieve a performance which is very close to the asymptotic base optimal solution. We also tested our algorithm on real graphs, where we had to test to measure the the goodness of the partition in terms of modularity, because we do not have in general a ground truth. And on all the data sets we consider, we obtained the highest, or in just one case, the second highest value of modularity with respect to the competing spectral methods. The modularity has been compared for the same value of k. It is, of course, a non-unique way of defining the goodness of the partition, but at least it evidences that we systematically obtain a better partition on the tested dataset in terms of modularity. So the algorithm we propose is also very solid on real graphs. We also have an interpretation, as I said at the beginning, of our work, of our algorithm, and of the competing methods in spectral clustering. First of all, let's start from the adjacency matrix. To obtain the beta Hessian matrix, we made the following path. We start from an Ising Hamiltonian, we make the beta approximation, we compute its Hessian, we obtain the beta Hessian matrix. If we do the same thing, but we perform the naive mean field approximation, then we obtain a spectral method based on the adjacency matrix. So essentially comparing the two is the same as comparing naive mean field with the beta approximation. The beta approximation being in general a better approximation because it is a second order approximation, which keeps into account the correlations, unlike the naive mean field. However, the naive mean field approximation is expected to give likely good results, especially on dense graphs, which is in complete agreement with the fact that the adjacency matrix has been introduced initially for spectral clustering on dense graphs. However, on sparse graphs, it does not achieve the alpha C threshold, and it does not keep heterogeneity into account either. Concerning instead the Laplacian matrices, what we can see is that I recall that zeta p is the hardness dependent regularization. Small values of zeta means an easy problem, whereas hard values of zeta, high temperatures, mean a hard problem. We had two different regimes. One was the dense case, in which we had the matrix D minus A, which corresponds to nothing but the optimal beta Hessian matrix in the trivial regime. So somehow, in this case, dense is a synonym of easy, whereas in the sparse regime, we had the opposite extreme. In fact, zeta p takes as the highest possible value the square root of rho b, for which the beta Hessian matrix was initially proposed. So we have these two extremes, which are the trivial and the worst case regime, and h of zeta p is the optimal hardness-dependent regularization. Similarly, we can talk about the regularized Laplacian matrix L tau, which is the matrix that corresponded to the black dots in fuselage earlier. To obtain this matrix, we just need to replace the degree matrix by the matrix d tau, which is defined by d, the degree matrix, plus tau, the identity. Then what we can see is that the beta Hessian matrix, zeta p squared minus 1, the identity, plus d, minus zeta p a, can be written as d zeta p squared minus 1 minus zeta p a, and relate the eigenvectors xp with the eigenvectors of the regularized Laplacian matrix. Then we can plot a similar graph to the one I showed before. For zeta p equal to 1, we have the trivial regime. The regularization becomes zeta p squared minus 1 becomes 0, and we obtain the classical regularized Laplacian matrix in the trivial regime. The worst case is tau equal to rho b minus 1. The optimal is tau equal to zeta p squared minus 1. And the black dots are the algorithm of Kinrohe, which proposed tau equal to the average degree, tau equal to c, which is close but not equal to the worst case regime, and as a consequence yields in general good performances but does not reach the detectability threshold, unlike L of zeta p squared minus 1. To conclude, we draw two bridges, one between classical and physics-based methods. We had a series of algorithms which were based on very different intuitions with very different methods, some inspired by math, some inspired by random matrix theory, some by statistics, some by statistical physics. And what we showed was that in the end, we can provide a unified framework to interpret and understand all of these methods under a single perspective. Moreover, we also saw how we can draw a bridge between the sparse and the dense regime. We used to have matrices that were good choices for dense graphs and matrices that were a good choice for sparse graphs. However, in practice, there is not a tight line separating these two regimes. When we have a real graph, how can we tell if it's sparse or if it's dense? Well, what we saw is that the matrices typically used in the dense regime are nothing but a limit of our proposed algorithm. So we expect that our proposed algorithm on dense graphs is nothing but recovers nothing but the typical choices of the matrix M. We also have a simple paradigm which starts from a cost function, which we call the Hamiltonian, and generates a matrix which adapts to the hardness of the problem. And this optimal regularization is computed and not estimated. We have an intuition that comes from the DCSBM, but it is well defined for an arbitrary graph for which we can compute the zeta p. Finally, we have a question. Is it possible to find the right temperature for a given machine learning problem? Even though this question is very wide and ambitious, we'll try to answer it in at least two examples. One is the extension to community detection in dynamical graphs, where we have a sequence of snapshots of the same graph at different times, and in which we expect that the community labels may change, but that they are correlated across time. So the idea is that if we run community detection at each time independently, we're not exploiting this correlation. Whereas if we consider the problem as a whole, we can exploit the correlation and improve the community detection performance. So what we did was to define a dynamical Hamiltonian. In this case, dynamical is in inverted commas because there's nothing dynamical about it. It's just the underlying model that is dynamical. We have two contributions. One in which the spins at the same time are interacting, and it favors configurations in which nodes in the same community have the same spin. And then we have another term in which each spin interacts with its own self at the following time, which is here in blue, and this introduces correlation. So we run the machine from the Hamiltonian, we obtain the beta free energy, we compute the Hessian, and we obtain a dynamical beta Hessian for spectral clustering. Here we show the overlap on the left of our proposed algorithm as a function of alpha, the hardness. Large values of alpha are easy problems, and eta, the correlation. So what we see is that the black line is the dynamical detectability threshold, which we are able to achieve for all values of eta, and large correlations allow us to achieve harder problems, so smaller values of alpha, unlike the competing methods in which a very large correlation is needed to obtain a good performance. Another application we gave is relating Nishimori to Bethe, as we called it. So we consider an Erdős-Rényi random graph, and we assign to each edge a weight which is distributed according to a symmetric probability distribution. And then we have a term which goes as e to beta n wij, where beta n is the so-called Nishimori temperature, which has great importance in Bayesian inference and physics of spin glasses. Then if we define beta hat as the largest values of beta, for which the smallest eigenvalue of the weighted beta Hessian matrix is equal to 0, the relation between beta hat and the zeta p should be evident. Then we claim that beta hat is a close approximation of the Nishimori temperature. We use this result to define a cost-efficient data clustering method. I would like to stress that here we're no longer performing graph clustering, but we really have data such as pictures of dogs and cats. Then we translate the problem of clustering these pictures into a graph clustering problem, and then we use our arbitration, and we obtain a very good results as shown in the picture on the right, as compared to methods based on the naive mean field, so essentially a weighted adjacency matrix or the weighted Laplacian. This is the list of the publications on which the works presented in this presentation are based on, which are 2 journal papers and 5 conference papers, 2 which in EURIPS, 2 in ICASP, and 1 in the French-speaking conference GRETSI. I thank you all for your attention and for having listened to me so far, and I wish you a good day.